problem. A pendulum is, you're given the mass of the bob of the pendulum, and you have the length of the thread, and so it's swinging in a vertical plane, right? All right, and it's released from rest, and when the thread makes this particular angle with the vertical, you're given the speed at which the bob is moving. So what we are told is that there is this pendulum, and it's been released from rest from a horizontal position. So the bob is tracing out this circular arc. When the speed of the bob is, so when the bob is in this position, you're given the angle that it's at right now. And you're also given the speed of the bob at that instant. And that's given to be 2.06 meters per second. Okay. And you're given the length of the pendulum, L. All right. It's probably easier if I just work in symbols. So it's just going to be V naught. All right. So the first question is asking.
Sorry, Professor, I just had a quick question.
Yeah.
So when we have a problem like this, how do we know whether they're asking for the angle on one side of the pendulum or the other?
What's the other possibility? Oh, why did I not draw it like this? You mean? Is that your question?
Yeah, how do we know if we're solving for, like, for example, if we're solving for theta or that angle that's next to theta on the right-hand side?
Or why is it not this angle? Yeah, it doesn't make any difference if you take this angle.
Okay.
Yeah, it doesn't make any difference at all. So you can pick either one. Okay. So I just randomly picked the right-hand side, but if you pick the left-hand side, it doesn't make any difference at all. So so we know the length of the pendulum. It's 0.25 meters. And we know the speed at which it's moving when it's making this particular angle, and that is 2.06 meters per second. All right. So the first question is asking, and you're given the mass of the bob. So this m is given. So the first question is asking, what is the magnitude of the bob's angular velocity omega and tangential velocity v? These are the two things that we need to find out in the first part of the question. Does anybody want to give that a try? So how would I find either of these, any one of these two?
Don't they already give you the velocity and the tangential?
Yes, exactly. So this 2.06 meters per second is nothing but the tangential velocity of the bob. That makes sense? So that is already given. So this Vt is simply 2.06 meters per second. That's exactly what the tangential velocity is. The speed of the object along its circular path. So that the speed with direction is velocity, and just the magnitude is just the speed. So we already know the tangential velocity. Is there any way I can find the omega from here? How would I find that? Look at all the relationships we've derived today. I'll write them down for you. So omega was d theta dt, and then v was r omega, and alpha was d omega dt, and a tangential was r alpha. So these are the relationships we derived. A centripetal is, what's the formula for a centripetal? It's long, we derived that a long time ago. V squared over r, exactly. All right, so yeah, so these are all the formulas we have. So is there any way I can find omega?
Yes, you can use velocity is equal to your radius times omega.
Yeah, v is equal to r omega. So omega would just be this v tangential divided by the length, which is the radius. That makes sense? The second part of the problem is saying, find the centripetal acceleration. So how would I find that? At this instant, when it's at this position, let's call it A. So how would I find its centripetal acceleration?
V squared over r.
Exactly. So the centripetal acceleration would be v squared over r. And what direction does the centripetal acceleration point?
Radially inward.
Radially inward, exactly. So that is the second question. The third question is, what is the tangential acceleration of the bob. So we know that this is, would you say that this is uniform circular motion?
No,
No. Why is it not uniform circular motion?
because our acceleration in the tangential is an acceleration.
There will be an acceleration in the tangential direction. And you also know that if you just from experience, if you swing a pendulum, you know that it's going to speed up as it's moving down, right? It'll be moving fastest at the bottom, and then it's going to slow down as it goes up and stop. So it's not moving with a fixed speed at all. So it's not uniform circular motion. So there must be an acceleration in the tangential direction. How do we find that acceleration? To do that, we have to use Newton's second law. And this is a calculation we've already done in chapter 5. So you've already seen this calculation. So to find the tangential acceleration, to find any acceleration in general, you use Newton's second law, because acceleration comes from force. So we just need to see what force is acting in the tangential direction. And from there, we can use Newton's second law and find the acceleration. So we're going to redo a calculation which we've already done in chapter 5. So what are the forces acting on the bob when it's at this location?
You have tension acting.
Yeah. And what else?
Gravity.
Tension, and what's the other one?
Gravity.
Gravity, very good. So just as we've done many times before, we are going to choose our axis. One will be in the radial, the other one will be in the tangential direction. Which force do we need to break into components?
Gravitational force.
Yeah. So mg, there'll be one component like this, another component in the tangential direction. That tangential component is the one that we are interested in for now, but we might as well just, as an exercise, we might as well just write down Newton's second law again. So this one will be mg cosine theta, and this one will be mg sine theta. Let's write down Newton's second law. F net equals mass times acceleration, both in the radial and the tangential directions. So let's start with the radial direction. So in the radial direction, can somebody tell me with the proper sign convention what equation I get? What's the F net part in the radial direction? This is all old stuff, nothing new here at all.
It's negative mg cosine theta.
Radially inwards is positive. Very good. So go ahead. Yeah. So I have that, and then anything else? Any other force in the radial direction?
Oh, and plus tension.
Exactly. So T minus mg cosine theta is equal to mass times, what's the acceleration in the radial direction?
Your centripetal acceleration.
Exactly, which is v squared divided by r. V is the instantaneous velocity at that particular location. V squared divided by r. All right, so I'll call it L instead of r, because that's the radius in this case. That makes sense? And in the tangential direction, we'll just choose this direction to be our positive direction, right? So can somebody give me the expression for Newton's second law in the tangential direction?
Would that be mg sine theta is equal to mat?
Exactly. So there is only one force in the tangential direction, and that is mg sine theta, and that is equal to mass times our unknown tangential acceleration. And so from here we can solve for the tangential acceleration, which is what this question is asking for, g sine theta. So you can see that the tangential acceleration is going to be g sine theta, right? And that's the answer. So at in this case is g sine theta, and it came from applying Newton's second law. Is everybody clear about that? So we have the Bob's tangential acceleration, that's part 3. Part 4 is asking for its angular acceleration, alpha. So how would I find alpha if I know its tangential acceleration?
Could you find it by dividing that tangential acceleration by our
Exactly, we would just use this equation right here. That alpha is a tangential divided by r, which in this case is L, right? So we found the angular acceleration alpha. The next part is asking for the total acceleration. How would I find that?
square root of AT plus AT squared plus AC squared.
Exactly. So the total acceleration means that the acceleration vector of which the two components are AT and AC, right? And so the total acceleration is simply AC square plus AT square. The magnitude of the total acceleration is AC square plus AT square, as we just saw in our discussion right here. So that's the total acceleration. The sixth part is asking for the tension in the cord. So how would I find that?
You can use the equation that you wrote down for Newton's second law.
Exactly. So that is not connected to this this chapter. It's a chapter 4 and 5 question. So I've already applied Newton's second law, and I found this equation in the radial direction. I could use this equation to solve for the tension. So the tension would simply be T is equal to mg cosine theta plus mv squared divided by L. So that was not related to this question, this chapter. And finally, another question that I just put in, it might not be in your version of the PowerPoint, is the velocity of the bob when it reaches the bottom. How would I find that? So I know the velocity of the bob when it's at point A. How would I know the velocity of the bob when it gets to point B?
Could you divide theta by the time it takes to get from A to B?
Well, that would give me an average speed, right? But I'm interested in the instantaneous velocity at point B. So how would I find that? Can we use anything from anywhere in the course? Maybe chapter 6 and 7?
Could we use like K naught plus U naught equals
Yes,
MU?
exactly. Absolutely. We can definitely use conservation of energy to answer that. So we know what its velocity is at position A. We need to find its velocity at position B. So we can set up conservation of energy. So I'll just draw a separate diagram over here. We know its velocity over here. We want to find its velocity when it gets to the bottom. So this is a chapter 6 and 7 question. How would we do it? Okay, so we need to know the difference in height. So let this height be h. This is L. This is also L, right? The radius of the circle. So K naught plus U naught plus W other equals K final plus U final, right? So the initial kinetic energy, what's the initial kinetic energy at location A? So this is just a review of what we did yesterday. So what's the initial kinetic energy at location A? In terms of its velocity, v naught.
1/2 mv naught squared.
1/2 mv naught squared. In terms of the height h, we'll choose h equals 0 at the level of B. So U is equal to 0 at the level of B. So in terms of the height h, what is the potential energy at location A? What was the formula for potential energy?
mgh.
Yeah, so it's going to be mgh, right? Is there any W other in this problem? No. The kinetic energy at B is what I'm interested in. So that's 1/2 mv squared, right? And what is the potential energy at B?
0.
0, exactly. So now I can solve for this V. The only thing I don't know is this H, right? Now, if you think back to the very first pre-lecture video that we had even before this course started, in the very first PowerPoint, there was a problem, a trig problem, where we actually calculated this H. And I would recommend that you go back and look at that or look at your notes for that if you've forgotten. But if this angle is theta, then this H, does anybody remember what this H comes out to? So it's just a trig question. So does anybody remember what this comes out to in terms of L and theta?
Is it L minus L cosine theta?
Yeah, it's L times 1 minus cosine theta. And I showed this in a lot of detail in that very first pre-lecture video. So that's a useful relationship. And so you can use that to get rid of H. And so you get 1/2 mv0 squared plus mg. Instead of H, you write L times 1 minus cosine theta is equal to 1/2 mv squared. And then I'll let you finish the algebra yourself over here and you solve for V. That makes sense? So that is how you can get the velocity when it reaches the bottom. And so the last two parts of this problem are just review of stuff that we've done earlier. Is everybody clear about this? The main point of this problem was to calculate all these quantities that we just discussed today.